Okay, so we just evaluated some indefinite integrals. Now we're shaking things up a little bit and evaluating some indefinite or some definite integrals. Just did indefinite, now we're doing definite. So these are basically like the indefinite integrals but with an extra step. So starting out, integral from minus 1 to 4 of minus x squared plus 1 dx. So what's the antiderivative? Minus 1/3 x cubed plus x. And because this is a definite integral, we evaluate this from minus 1 to 4. Remember, this line with the minus 1 and 4 says, plug in the top thing, subtract what you get when you plug in the bottom thing. So we get minus 1/3 x cubed plus x, evaluated from minus 1 to 4, is equal to minus 1/3 4 cubed plus 4 minus 1/3 times minus 1 cubed plus minus 1 equals minus 64 over 3 plus 4. Minus 1 cubed is minus 1 times minus 1/3 is plus 1/3. And I have minus 1 but minus minus 1. So plus 1. So I get minus 63 over 3 plus 5. Minus 63 over 3 is minus 21. Plus 5 is equal to minus 16. And that's our final answer for part A. Next, on to B. We want to integrate from 0 to pi over 3 of cosecant squared of y dy. So how do we do that? So the antiderivative of minus cosecant squared is cotangent. So I'm going to rewrite this as minus integral from 0 to pi over 3 of minus cosecant squared of y dy, which is going to be equal to minus cotangent of y evaluated from 0 to pi over 3. Now we plug in. We get this as minus cotangent pi over 3 minus cotangent of 0. Okay. I was not as careful with this as I should have been. So here's another change we're going to make. Make this a pi over 6. Pi over 6. Pi over 6. So I'm going to edit that, change this integral so it's pi over 3 to pi over 6. It doesn't change what our antiderivative needs to be. That's still cotangent. I just need this to be a pi over 6 because this function is not defined at 0. Okay, so minus cotangent pi over 3 minus cotangent pi over 6. So this is writing it out minus cosine pi over 3 over sine pi over 3. Minus minus is a plus. Cosine pi over 6 over sine pi over 6. Cosine of pi over 3 is minus 1/2. Sine of pi over 3 is root 3 over 2. Plus cosine pi over 6 is root 3 over 2. Over sine of pi over 6 is a half. I'm dividing the top and bottom on both sides by 2. So I can cancel those. If I multiply by the reciprocal, you can think that way the 2's would cancel. So this is minus 1 over root 3 plus root 3. I can simplify this, minus 1 over root 3. I can multiply by root 3 over 3. Root 3 over root 3. And I get minus root 3 over 3. That's not the thing I wanted to multiply. Multiply this thing over here. That'll make this slightly easier. So I have minus 1 over root 3 plus 3 over root 3 equals 2 over root 3. And that's my final answer there. Okay. So, part C, integral from minus 1 to 1 of x times 2x squared plus 3 to the 5th dx. So what should I do here? I see 2x squared plus 3 to the 5th. That seems like it'd be really difficult. In theory, I could expand it all out and use the power rule, but that seems way too hard. So instead, I'm noticing I have 2x squared plus 3 in parentheses. I have an x in front, so this should be a u substitution. So let u be 2x squared plus 3. Du would have to be 4x dx. So this integral becomes integral. And first things first, I want to change these bounds. So u of 1 is going to be 2 times 1 squared, which is 2, plus 3 is 5. U of minus 1 is equal to the same thing, 5. So I have integral from 5 to 5 of x times 2x squared plus 3. Sorry, not this anymore. So I have this 2x plus 3 as being u to the 5th. I will write this x here, and I'm going to write dx equals du over 4x. So this becomes du over 4x. The x stuff cancels. I get 1/4 integral from 5 to 5, u to the 5th du. And actually, we could have stopped this quite a bit earlier, but this is to make sure this u substitution works. So we have a rule that says if you're integrating something from a to a, from a number to itself, then that should always be equal to 0. And that's what we have here is we plugged in 1, we went to 5, we plugged in minus 1, we got to 5. So altogether, we didn't really have to do all the work. We could have used power rules, substituted back in, but this is another reason why I prefer the method of changing bounds, because we just simplified what we had to do considerably there. Otherwise, you would have gone back to x and then figured out, oh, okay, when I plug in 1, that's the same thing I get as when I plug in minus 1. And that's to do with the fact that this is an odd function. Moving on to part D, we have integral from 0 to pi over 2 of cosine r square root sine of r dr. So here's another u substitution. I see sine inside of a square root, so that's my first thought is if I see one function inside another, that's my first guess for a u substitution. Let u be equal to sine of x. Then du is equal to sine of r. Du is cosine of r dr. So then this becomes integral, same thing, need to find new bounds. U of pi over 2 is equal to cosine pi over 2 times root sine pi over 2, which is equal to 0. And then u of 0, we're going to see something similar, is cosine 0 root sine of 0. Sine of 0 is equal to 0, so we get integral from 0 to 0 of of square root of u. And let's pretend like we didn't remember that rule from last time. Let's evaluate this like we normally would. We're going to get, this is u to the 1/2 du. This would be equal to 2/3 u to the 3/2 evaluated from 0 to 0 equals 2/3 times 0 to the 3/2 minus 2/3 0 to the 3/2. And these two are the exact same thing, being minus, so they cancel, equals 0. Okay. Next, integral from 0 to 1 of x squared plus secant x tangent x dx. So this one's kind of like a breather. This is the same thing as integral from 0 to 1 x squared plus integral 0 to 1 secant x tangent x dx equals, from the first part I get 1/3 x cubed. From this part I get secant. So the left integral gives me 1/3 x cubed. The right one gives me secant. And then I evaluate this from 0 to 1. So this is 1/3 times 1 cubed plus secant of 1 minus 1/3 times 0 plus secant of 0. Doing just a little bit more that we can. This is 1/3. Secant of 1 is cosine 1 over, or is 1 over cosine 1. But that's not a nice number on the unit circle. So we just have to leave it like secant 1. Plus secant 1. 1/3 times 0 is 0. Secant of 0 is also 1. So I get 4/3 plus secant of 1. And that's the best that I can say because I can't find an exact value for secant of 1. If I were using a calculator, I would estimate this to 2 decimal places. F. Integral from 0 to pi over 10 of 10 times cosine of 5a dA. So here this is one where I almost know what it is. The integral of cosine is sine, but that 5a is messing with me a little bit. So let u equal to 5a. Then du is going to be 5 dA. So how can I fix this? I get now integral, if I plug in my upper bound, pi over 10, I get 5 times pi over 10, which is pi over 2. And I wrote 10 when I meant 2. U of 0 is 5 times 0 equals 0. And now this 10, I need 5 du's. I have 10 of them. So this becomes 2. 10 divided by 5 is 2. Times cosine u du equals 2 sine of u evaluated from 0 to pi over 2, which makes this 2 times sine pi over 2 minus 2 times sine of 0 Sine of 0 is 0. Sine of pi over 2 is 1. So this gives us just 2. And that's all there is to that. One last problem, and this one is tricksy. So what is the trick? FG. So we have the integral from 1 to 4 times root 1 plus t squared times t to the 5th dt. So here we have to use use substitution, but we have to be a little bit clever. So let u be equal to 1 plus t squared. Then du is going to be equal to 2t dt. So we have this weird situation where I have a t to the 5th though. So how am I going to fix that? The answer is this way. I'm going to take a t, so I'm going to make this square root 1 plus t squared. I'm going to take a t out of the t to the 5th, so I get the t dt that I need. And I'm going to look at this t to the 4th and say, wait a minute, if u equals 1 plus t squared, I can rewrite this equation as t squared is equal to u plus 1. T to the 4th is t squared squared is u plus 1 squared. So this integral becomes integral from, and now I need to change my bounds. U of 1 is equal to 2. U of 4 is equal to 17. So integral from 2 to 17, square root of u, t to the 4th we just said was u plus 1 squared. And then the t dt, I need 2 of those, I only have 1, so I can just put in a 1/2 du. Okay, so now we've got more work to do. This is equal to 1/2 integral from 2 to 17 of, write it u to the 1/2 u squared plus 2u plus 1 du equals 1/2. Now let's do some expansion. This becomes u to the 5/2 plus 2u to the 3/2 plus u to the 1/2 du. Integrate each part, you get 1/2 2 over 7 u to the 7/2 plus 4 over 3 u to the 5/2 plus 2 over 3 u to the 3/2. Evaluate that from 2 to 17. Neither of these are nice numbers, so I'm just going to have to leave them in terms of rationals. So this is 1/2 times 2 over 7, 17 to the 7/2 plus 4/3, 17 to the 5/2 plus 2/3, 17 to the 3/2 minus 2/7, 2 to the 7/2 plus 4/3, 2 to the 5/2 plus 2/3, 5 to the 3/2. And that's how it goes. So this one was really tricky, probably harder than what I would be willing to put on an exam, but still a good example of this idea with use substitution.